Well, so today we'll carry on our quest to solve all problems in the subsurface. You remember that we talked about the idea that we're going to choose the most difficult problem to work on, and that is, say, contamination of aquifers by non-aqueous phase liquids. So non-aqueous phase liquids travel on their own. They might be gasoline that gets cupped in on the water table, or they might be denser than water, so-called NAPLs, that will migrate through the water table down to some capillary barrier, such as we suggested here, and leave a trail, a chimney or a trail as it goes through. They might have some interesting architecture that develops, and we suggested that this interesting architecture was because these are low permeability layers, but it's actually not permeability that makes them special. They're special because low permeability materials have very small pore spaces, and those small pore spaces can't be penetrated by the non-aqueous, the separate fluid, the immiscible fluid, which is trying to break a bubble into that very small capillary. As the capillaries get larger, then the bubbles can go in, and they can go straight across these layers. And of course, that would be the case for this so-called aquitard. It's not really an aquitard. We'd probably be better off calling it a capillary barrier, a barrier that resists by capillary forces to stop things coming through. And so that's kind of the place where we are. Last time we talked about thinking about individual capillary tubes, and I guess I can draw it on here. I'll just move this up. And so in terms of, I always like doing this recap thing. It's kind of, you may find it a bit pedantic. But you remember that we talked about these geometries. We talked about single capillary tubes. I'm just going to remind us of the equations that we had that describe these. Probably straightforward to do that. Most of the notes you have on this this big compendium. Perhaps this one, you certainly have what we're going to talk about because we talked about it last time. And you remember that we talked about the idea of height rise, H sub C. If this is water, this was an aperture. This was a diameter, I guess. And this fluid that we'd have rising up, this would be the same fluid that's here. God, I should be an artist. I am an artiste. And that we could get, I just jotted down two equations for height rise. The height that it rises is 4 times the interfacial tension divided by the diameter of the capillary tube and the unit weight of the fluid, whatever that is. And that's the same as in for this kind of parallel plate example, which differs only by a factor of 2 to 4, and it's the aperture of the fracture multiplied by the unit weight of the fluid. Unit weight is just density times gravity, you know that. And so what we could also do is we can use this to get what we refer to as a capillary pressure. Which is equal to, by definition, the pressure in the non-wetting minus the pressure in the wetting. Let me come back to that. And that would be equal to unit weight times HC. And so the capillary pressure for these, if we were to write it out, would be just these terms here divided by, multiplied by unit weight. So the capillary pressures would be 4 times interfacial tension divided by the diameter. And for this other geometry, whoops, it would be 2 times the interfacial tension divided by the aperture. And so that's interesting because what it allows us to be able to do is it says that this height rise is going to be big if we have a big interfacial tension. It'll climb a long way up. It'll be big if we have a small diameter, as you know how capillary tubes work. But the meaning of this is that this is just, we're choosing this arbitrarily. This is the pressure in the non-wetting fluid and the pressure in the wetting fluid. So I guess I can try and be very smart about this. And if I'm smart, then what I could do is I could take the pressure that's acting in the wetting fluid, and I could take the pressure that's acting in the non-wetting fluid. So we said before that typically in our systems, if these are glass plates and they're quartz in a reservoir, so the wetting fluid would be water, and in this particular case this is just air. So this is, well, I guess it's air, it's mainly nitrogen. And so we're making the point that there's a pressure difference across this boundary. Has to be the case. We can rationalize it because what we know about this system is that if we look at the pressure versus elevation. Oh, I like this thing on the side. I've never had it before. Right? We know that, what do we know? We know that the unit weight of fluid is equal to the rate of change of pressure with elevation. Negative sign because we usually have Z going upwards, but we don't in this case. And so if we look at what this would be, then this is dP, this is dZ. So this would also be, these are the same, right? So this would also be equal to unit weight of fluid and 1. That's the other way, how we always thought about that before. And so the curious thing about this is that if we look at this elevation of this interface, I guess perhaps it would be this elevation right in the middle, then if we project this up to that point here, then this length here is equal to what we're calling capillary pressure. That's really all it is. Physically, that's what it means. And so it's fine to have these equations, but you should realize exactly what those equations mean. So this is saying that the difference between the pressure in the wetting fluid and the non-wetting fluid, air, is finite, and it's equal to, it's kind of equal to the height rise of this. And the reason for that is that we know that at this point here, since we can draw that directly to the outside, we know this has to be atmospheric, which is 0 pressure here. And so we know that this has to be a negative pressure. It has to be in tension. So what it's saying is that this surface, by its curvature, is in tension. Actually, you can think of it kind of like the cable on a suspension bridge, right? You know, a suspension bridge is in tension. It's got the deck hanging off it. And the reason it's in tension is because it's holding that stuff up. That's exactly what this is doing. It's holding up this interface through this tangent to the boundary here. And therefore, we can divide that. So that allows us to make a rationale of what we've done. So this means now that when we referred to this, I don't really, yeah, I'm going to go back to our figure here. And if you recall that we talked about this interface here, or perhaps I have to go back a long way, but you can make the case. Oh, this, right? We talked about this geometry here. And so the definition, if you took 452, the definition of a water table is that here the pressure is equal to 0. If you measure pressure with depth, that we just did, then by definition the pressure at this point has to be 0. It has to change according to it has to change according to what we said before. I see people's eyes straining. Is my writing bad and poor? So this would be unit weight. This would be 1. This is the gradient of groundwater pressure, just like going down in a swimming pool. But what this allows us to do is, if we want to, we can extend this back up to the surface. And that says that in this zone here, the vadose zone, the tension saturated zone, it's saturated by tension. This is a negative pressure that it has in here, and it's because of this capillary rise within the system. So that's physically what's going on. And so our interest in this is to understand multiphase flow where the system is water and air in the vadose zone, but it's also to understand multiphase flow where the system may be water and NAPL both taking up the same pore space. And so we can use these concepts of capillarity to be able to say something about that. So that's kind of where we're going with this. So the other figure that we have, let's see if I can find it. So if we go back to this, it's all well and good to define things in terms of these capillary tubes, but what do those physically mean when you talk about what we said last time, a representative elemental volume? And so what we could do is we could take a volume here. Oh, let me blow it up. So we could take a volume here. Probably can't see the green very well on this, but I'm just trying to make the case that instead of a bundle of capillary tubes, which this really isn't, kind of is in the pore spaces, what we might like to do is find a general relationship that says something about what this capillary pressure, P sub C, is within this as a function of saturation. And so that's kind of the approach that we'll take here, is instead of trying to figure out exactly what the behavior is by using lots of little capillary tubes, what we could do is take an experiment, take a block of soil, put it in some kind of apparatus, push some fluids into it, measures the pressures of those fluids in aggregate, and then use that to say something about what the height rise would be in this system. That's what we were attempting to do. And the relevance of that is, I guess you can see it in two ways here. Have we looked at this? Perhaps we didn't look very much at it. If I take so I guess what do I, none of these are going to show up very well probably, are they? So what we could do is we could look at an REV that, for instance, included this. And we said something before about saturation, right? Saturation is kind of roughly the relative areas of red versus light blue. And so the saturation of, you can't see that, the saturation of red would be, I don't know, 15%. The saturation of blue would be, by definition, 85%, right? Because they have to sum to 1. So that would be one way of thinking about an REV, representative elemental volume. Or we could take an REV that was in here. And in this particular case, the saturations to red would be, I don't know, it could be 100%, but let's assume it's not 100%. Let's say it's 95%, and the saturation of blue is therefore 5%. Again, right, because they have to sum to 100. And so we could think about this in two ways, right? This is a bit more like our single capillary tube, right? We know exactly why fluid has gone down here. It's gone down the biggest pore space because it can get in there. There's no exclusion from entry into the pore space. And this stuff up here must have smaller pores, so it can't get the red fluid into there. But what's going on here? Well, we said last time about the relative saturations that the water would coat the particles, and it would have what we called pendular saturation. So where one particle joins onto another, there's a ring around it, a donut or a torus, which is the covering of the particles in water, but also a bit more water at the edge. And so clearly within here, it doesn't really look like our capillary tube, but it has the same kind of behavior. And so what we'd like to be able to do is we'd like to make a relationship that gets the saturation of this water as a function of capillary pressure. And I think that was the kind of parting shot that we had last time as we parted from each other. So that's our goal here. So instead of using an individual tube, which is useful as a construct to be able to kind of understand things like this, but we want a more general relationship which is able to describe our system. So that's what we're going to do today. So that's our plan. So I will go back to this. I'll go back to this. Don't mean to give you whiplash. We'll talk about all kinds of stuff. But, yeah. So this is, remember this? Pendular saturation. Grain on grain, coating of white water on the grains, but also a pendular ring as you go around it. And I think this is actually, what a segue. This is exactly the statement I made before we parted. We'd like to find some relationship between how much oil there is in here and how much water by proportion, and what might be the differences between the pressures, which we can use to index that. And our interest in that is because it allows us to say something about when a capillary barrier will act as a capillary barrier, or whether it will let the stuff directly go through. So we're 30 minutes in and we're just getting to the first slide. But that's okay. We have plenty of time to do this. So that's what I'm going to do. So that was the recap, probably more lengthy than it needed to be. What we would like to do, I think what I'll do first is I'll talk about this, because this is the subject of your second assignment, and it's relatively straightforward to understand exactly what's going on. How do we make this relationship between saturation of water as a function of capillary pressure? How do we get that? Well, we measure it somehow. So let's cut to the chase and do that straight away. It's not really in the right order for these things, but it's a useful way to introduce it. Hopefully I can find it. Oh, there we are. So a so-called Welder Apparatus, as in this individual here. And so it's quite straightforward. The idea is this: you take a core of your sample core, you place it on a frit which only has a very specific pore size, in which case it will let the fluid that's saturating the core into here, but it won't let the fluid around it into it. And so what you would do is you would fill your core with water. You would put it in this apparatus. You'd top up around it with oil, your non-aqueous fluid, and then you'd apply a nitrogen pressure to be able to overpressurize this hashed fluid higher than the pressure in here. The pressure in this core can only be, by this manometer, the same as the pressure in this column. And so by increasing the nitrogen pressure that you apply in this stippled fluid, what you'll do is you'll force this other fluid to start invading it. So if this was the red fluid that's around here, then it'll find some pathways into here, and it will start having some little rivulets in it. Right? And so what you could do, and I'll do it on the same scale, you could make a plot of saturation of water and if there's no water in it, there has to be something else. It would be NAPL. And if it's 100% saturated with water, then there can be nothing else in it. So it starts out at 100% saturation of water. And on the vertical axis, this capillary pressure. You can think of the capillary pressure essentially as this nitrogen pressure, that's all, this overpressure, relative to the air pressure. Because the pressure in here is going to be very small because it's governed by this height of fluid, and it's essentially the nitrogen pressure. So this is essentially equal to what we call capillary pressure. And so you start off with no pressure, and you'd be 100% water saturated. You'd increase the pressure a little bit, and the pressure would not be large enough to be able to get stuff to go into your sample. And so you'd increase the pressure up to some amount, and it'd still be 100% water saturated. Increase it some more, still nothing happens. Then at some pressure that you go up to, all of a sudden you get portions of this sample being invaded. If it's got red fluid in it, it can no longer be 100% water saturated. So whatever your new pressure is, then you have to be at least a little bit NAPL saturated, which is this point here. So it would start off here as you raise the pressure. You'd put the pressure up to here. It would slowly trickle in, and then it would stop trickling in when it reaches equilibrium. You'd up the pressure again to get to this point, and some more stuff would trickle in. So it would become more saturated with the NAPL, and you'd end up at this point. And you just keep on doing that. And so now what you have is you have three curves. Certainly 100% water saturated, certainly 100% water saturated, certainly at this point 80% water saturated, say. But what are these intermediate points? Well, you don't really know exactly what that is, but if you drew a line that went through these points, not doing a very good job of this one, this would be a line that says something about how the capillary pressure has changed and how the equilibrium saturation has changed at each of these 3 points. You don't have the information between, but you can extrapolate it. You could get the information by just going up very small steps, right? If you wanted to, you could just go. If you wanted to do this, you could do, right? But you might be in the lab all hours of the day, and you'd probably prefer to be in the bar. Why not? And so you come up to here, and you'd find out that ultimately this curve, not doing a very good job, this curve would go vertically. And I'll put it back to this. Oh, that's a thick one. This is the redder one. So now you have a given pressure in here. It's quite red, it's quite saturated. You can see from this here that if you went down here, this would be something like 30% saturated with water. If it's 30% saturated with water, that's not a 6, that's a percent. Then it has to be 70% red fluid, if you like, which is the NAPL. And so now what happens if you back off the pressure that you have here? So you decrease the pressure. And so just to make it clear, maybe I'll use a different color. So you decrease the pressure responds to get to this point. You decrease it again. The pressure goes to this point. And you decrease again. And pressure goes to this point. So the only ones we're interested in are this one, this one, this one, and this one, because they represent the equilibrium pressures. Once it's reached equilibrium, you know, the fluid will creep in on this curve, the so-called drying curve. Drying curve because you're drying water out of here. the fluid, the water will then creep back in once you go down this curve, the so-called Inhibition Curve. And if you join these points up, then you'd get a curve that looks like this. So bad drawing, but you get the picture. The point is that the test is very, very simple. You just try and replace one fluid in the core with another fluid. You do it by changing the pressure that you push it in with. If you can measure the pressure you push it in with, and you can measure the change in saturation, then you have this curve. And of course, any fluid that comes out of this core can only go into this tube. And so just by measuring how much this comes up the column gives you a direct measurement of the volume change within the sample. And so you're able to construct this curve exactly from that. And so that's what we'd like to do. We've achieved our aim, if you like. We wanted to determine how saturation of water changes as a function of capillary pressure. We've controlled the capillary pressure and we've measured saturation. All we need to know is what the pore space of this is. So what is it? The porosity equals the volume of the pores divided by the volume total. The saturation is equal to the volume of the fluid divided by the volume of the pores. And so if we know exactly what so I guess we could rearrange this as being equal to porosity times the total volume of the sample is equal to the velocity of the pores. If we throw this in here, then we get saturation is equal to the volume of fluid divided by the porosity and the volume total. So we want to know what saturation is. We know what the porosity is. It's a physical property that won't change. Maybe it's 10% or 30%. We know the total volume of this sample because we can physically measure it. And if we measure the volume of the fluid as it comes up here, we know the change in saturation. And so de facto, we can measure how saturation changes as we apply this pressure. And so we have this relationship. That's it. Clear? Crystal, as they would say. Crystal clear. So okay, so that's the last of the things that we wanted to talk about. So let's go back logically and look at the precursors to that. And so I guess we've done this. And so what we'd like to be able to do is maybe look at what the features are of real capillary pressure versus saturation curves. And there are a couple of approximations or characterizations we can use, one named for Leverett, one named for Brooks and Corey, a petroleum engineer, agronomists from Colorado State, I think, and explain some of these terms, exactly what they mean. This is, I'm going to look at the best one of these figures, I think. I'm trying to, do I have a better figure? This is the best figure. Right. So this is if we do exactly what we just said we did. This is the best curve that can perhaps explain all of the features that we want to explain. This is a capillary pressure versus saturation curve. So I'm going to erase this, but we've done exactly what we said we'd do. We'd raise the pressure. We'd raise the pressure again, and then it goes across to bad drawing. So we've made this curve by doing exactly what we just previously did. That's exactly where this curve has come from. I'm going to erase that, just complicates it. But we've made a curve that is our so-called drainage curve. Drainage because water is draining out of the system. These were first developed in agronomy. So if you have a crop, soil in a crop, you drain the water out of, you talk about draining water, you don't talk about draining air typically, right? And so that's the reason for that. So if we point out the features of this curve, let me just highlight each of them in due course. The drainage curve. The drainage curve occurs when you push air into the system. You slowly, at the detriment of air, push out water. 0% water saturation, 100% water saturation, 0% non-wetting air, and 100% non-wetting saturation. So these are the exact opposite of each other, obviously. As you start with 100% saturated and you push air into the system, you go up the drainage curve. You see that as you get more and more air into the system and more water out of the system, you see it as asymptotes to this very steep curve. It's saying that no matter how you try to push more air into it, you can't get the last bit of air. No matter how much you push air into the system, you can't get the last bit of water out of it. And that's because you have this pendular saturation. You can get it out of the big open pores, but when you get down to very low saturations, you have grain on grain, you have a monolayer covering of water in the grains, and you have this pendular ring at the contacts, which has a very tight radius of curvature, and it means it doesn't come out very easily at all. And so you end up with this asymptote, and this asymptote is important because it's referred to as the irreducible saturation of water. SW0, which you see written right here. And this is saying, try as you might, you can't get more of the water out of the system than this. And the water is our wetting phase in this particular case. So you go up to here. Now you start backing off the gas pressure that you've added to it. So as you back off the gas pressure, then you come down here. This is an atmosphere, it's a pressure in this case. So as you come down here, you come down on a second curve. The curve that you come down on is the inhibition curve, which I'm covering in blue, if you can see it, not very well. This inhibition curve says that as you back off the pressure, if there's any fluid sitting on the outside of this material, it just sucks it in. It imbibes it because it's attracted to it. It loves the quartz. It's quartz-philic, not quartz-phobic. And so it comes on to cover the quartz and keeps on going in. And so that increases by doing exactly what we've done before. Remember, we drop the pressure and you'd reach an equilibrium saturation. You drop the pressure, you reach an equilibrium saturation like this. Ultimately, you get to this point. And this point represents another important feature. This is the irreducible saturation of the non-wetting fluid. This would be wetting. H2O is synonymous with wetting. Non-wetting would be either our air or our NAPL. That's important. And this says something else. This says that no matter how much you back off the pressure, you won't get back to the initial saturation of 100% water saturated. You're left always with some amount of fluid in here. And so if you think about what this looks like, then it looks like exactly the picture we looked at before, last time. This is the water wet sand. This would be 80% filled with black NAPL and irreducible saturation of water. The red stuff here would be water at 20%, 30% I think we said, and oil at 70%. As you push out so this would be air, the black stuff would be air in our particular case. And as you reduce the amount of air that's present within the system to get back to 100%, then you're left with some bubbles of air or oil within the system, which are, so if you look at this figure that we had before, very schematic form of this figure is this. These are these two kind of no-go lines that we have. This is saturation of water irreducible. Saturation, I realize that's pretty thin. Oh no, you can see not too bad. Irreducible saturation of the non-wetting fluid. So this case here would be here. And this case here would be there. That's all. That's all this is describing. But what it allows us, and I should put units on it, and you should ask me to put units on, capillary pressure versus saturation of water. And so that kind of explains what we're attempting to do. So now we're trying to take this schematic of what's going on, and we're trying to put some numbers on it to define how the saturation changes as a function of the pressures we apply. And the reason for that is it allows us, if we can measure this curve, to say how much the thickness of oil might be before it breaks through the capillary barrier that it's sitting on. That's the practical application of this. So, okay. So there are a variety of ways we can think about this. Don't want to overstay my welcome again. So let's go back to this one curve. Any questions? You should shout if you want to ask questions, because if you know anything about my style, is I just don't stop. So break the rhythm if there are things you don't understand, and you can always go back to these after the fact. All right. So drainage curve, draining water. Inhibition curve, imbibing water. The limits on saturation is an irreducible saturation of water, irreducible saturation of the non-wetting fluid. Actually, those are the main parameters that we need to understand in this class. The other thing that I guess we might be interested in are these so-called scanning curves. The idea of that is that if you went up this curve to one of these points here by increasing the capillary pressure and found yourself at here, if you then drop the pressure at that particular point, instead of going somehow over to here and down, you go on this scanning curve. It's kind of a hysteretic curve. And that allows you to kind of map between this drying curve, the drainage curve, and the imbibition curve, and you'd go from here down this curve here, and then back along this curve to this point. So hopefully it makes some sense. And the ramifications of this is that if you think about it, this would be a saturation of NAPL, or non-wetting fluid. Let's just call it non-wetting. And this would be a saturation of water. And here, what is it? It looks like it's about 28%. In other words, the distance from this axis to here. And this one looks like it's 12. I don't know, 90 would be there, right? And so this is 88, 87. So this would be equal to 12%, 13%. And so the utility of this would be that the mass of the fluid is equal to the density of the fluid, the volume of the sample, the porosity, and the saturation. Right? So the volume of the sample times porosity would be, this would be the volume of the voids. In other words, the pore space would be the product of these two. The void space is filled by a 12% saturation, so the amount of fluid within the pore space is equal to 12% of that total pore space. You'd use a decimal rather than 12%. And then if you multiply by the density of the fluid, If it's gasoline or air or water, then that gives you the mass of that fluid. And so, straightforwardly from this, we can find out something we're interested in, but also we can say something about the form of this curve. So what we will find is that we'll use this curve ultimately, and I won't stop here, or I won't say here. I don't know if I've got an easy figure. No, I won't do it now. So, sorry. There are ways that we can characterize this curve. So this is what this curve is. And so it's relatively complex, I suppose, because it has a curve here and a curve there. It's not a particularly straightforward curve for us to characterize. We perhaps are going to use this a lot, and we will use this a lot. So we might want to be able to characterize this in some simple way. And so there's a couple of simple ways we could think of, and those are the two titles that we have here. We can use the concept of a Leverett curve to do it, or we can use the concept of a Brooks-Corey curve to do it. And they're both quite straightforward. We've done drainage and inhibition already. And so this is the idea. The idea is that if you look at this figure here, it looks a bit like the two curves that we drew down the notes a little bit. We have the same features for these. We have an irreducible saturation of water. We have an irreducible saturation of the non-wetting fluid, this point here, where this intersects here and this intersects here. So we have those two curves. We know this is the drainage curve. We know this is the inhibition curve. And we also have something else which is quite important for us. We have this term here, which I didn't define on the other one, but it's called PC0 or P bubbling. We'll call this the bubbling pressure. And so what this is saying is that when you apply a pressure of air to get into this saturated sample, the air can't go in initially. It only can go in once that bubble of air is small and is under enough pressure to find its way into the smallest possible capillary, the largest possible capillary that's available to it. So when the air pressure acting on the outside of this water saturated core is large enough to force its way into the biggest capillary that's there, still a very small capillary, then it will start invading the sample. If you then apply a bigger pressure, then it will start finding its way into progressively smaller and smaller capillaries in the interior of the sample. That's physically what this curve means. So this would be a very big capillary, this would be a smaller capillary, this would be an even smaller capillary. So that's physically what this curve means.
I have a question.
Yep.
What's bubbling pressure?
Sorry?
What's the bubbling pressure?
Bubbling pressure is the pressure that you have to apply to push a bubble of air into the sample. And so if you can think of it, I have a figure of it in this, I'm sure, but I haven't used, I can draw it. So in other words, bubbling pressure is if you take, never mind a grain system, if you apply a pressure at this upstream side in a reservoir of water, initially as you apply this pressure, nothing will go into this capillary. If the pressure is big enough, you'll get a bubble of air going into the capillary and will be able to displace all the way down. So it's the pressure at which a bubble first goes into the capillary, or in this case into a porous medium. So, thanks. So the important features on this: bubbling pressure or entry pressure, capillary entry pressure, drainage curve, inhibition curve, irreducible saturations of water, and irreducible saturations of the non-wetting fluid. Those are the features of it that we might want to use. However, this number for the bubbling pressure is useful for us to be able to say something about, it exactly says something about It exactly says something about the height to which this column can be carried on this lens of stuff. If the bubbling pressure is very big, then this height will be large. If the bubbling pressure is 0, then this lens will not exist. This NAPL lens will not exist. So it's useful for us to be able to do that. But it's not very easy for us to be able to measure that parameter in an experiment, as it turns out. And so what we might like to do is figure out exactly what this is. It turns out that what we can do is we can define this graph not in terms of water saturation, and this was capillary pressure. Well, P sub C equals capillary pressure. Instead of defining these axes, this being capillary pressure in this direction, this is 0 and this is a big number. This is saturation in this direction. This is 0 and this is 100%, or 1 if we're decimal. What we could do is we could take the capillary pressure and we could divide it through by some parameters. And the parameters that we'll divide it through are to make it into a non-dimensional number, and that non-dimensional number defines the so-called Leverett curve, and those this will be capillary pressure, this will be porosity, I think these are defined in this thing. This will be interfacial tension. How, the stickiness, the thing by which bugs walk across the surface of a lake. And this is permeability. Which we haven't defined yet, but you'll know what permeability is from 452. So the point is that if we non-dimensional this curve, this bubbling occurs always at an order of about 0.3. So when this invasion occurs, the magnitude of this should be about 0.3. In other words, this ordinate here. And that's kind of useful, because if for our porous medium we know what the porosity is, if we know what the permeability is, which we quite often know, can measure it quite easily, and if we know what the interfacial tension is of the fluid that we're trying to invade it with, then we immediately know what the entry pressure is that it can sustain. So from this equation, the only parameter that we wouldn't know would be the capillary pressure, which of course is this curve. And if we wanted to know this very distinct capillary pressure here, when the bubble first goes into the porous medium, that's the same as the bubble being excluded from going into this lens. And so we'd be interested to know exactly what this is. And so if this curve always looks like this, when we plot it as a J function, then that's great, because we don't have to go in and measure it very reasonably. And we always know that this value here should be about 0.3, and if we want to, then out of this we can pull out the value of this capillary pressure as entry pressure. So that's one convenient way of us being able to look at it. The other thing is, so we can always use this curve, this form of this curve as a template to be able to think of this response for any material. Clay, sandstone, fractured rock. This is probably not a bad template for us to be able to use, so maybe we can get away with never doing an experiment ever again, at least for capillary pressure. We might want to have to measure permeability. The other thing about this is, though, that it's not very convenient because it has, it's a complicated curve. And so one other thing that we could do is we could try and convert it to something that's much easier for us to accommodate, and that would be this Brooks-Corey relationship. And the idea is that we can take this same curve, but instead of plotting it in terms of a capillary pressure and a saturation on a normal scale, we plot it against saturation and a capillary pressure on a log scale. And we plot saturation a little bit differently because we choose it relative to this saturation here being equal to the zero saturation. So the irreducible saturation of water we use as the zero saturation. And if we do that, then the punchline is that this is what the curve looks like originally. This is the bubbling pressure, which we said was 0.3 for the Leverett curve. This is the saturation on the bottom. This is the drainage curve. This is the imbibition curve. We've kind of drawn them together here. Let's only look at the drainage curve, which this really is. This asymptotes to an irreducible saturation of water. So what we could do is we could define an effective saturation, which is equal to the water saturation minus this irreducible saturation of water. So this term on the top would be this magnitude, starting off here as 0 and going in an amount SW, right? So we go in an amount, this is SW, this amount is SW0, and so this amount here is SW minus SW0. That's physically all that is. So this term on the top is that. And this term on the bottom is just 1, which is all the way across here, minus SW0. So in other words, this term, when I do it in blue, this term on the bottom is equal to this length here. One minus SW0 is this. And this term on the top is equal to just this. So all we've done is we've changed the measure of the saturation relative to the 100% saturation just by lopping off this part, which we don't care about. And so if we plot an effective saturation, which is really what this is, and if we plot a pressure divided by unit weight, PC divided by unit weight, what the units of that have to be units of length, right? Meters. Capillary pressure is newtons per meter squared. Unit weight is newtons per meter cubed. So it's units of length. So this is just a height of the head, water. And if instead of plotting them as capillary pressure and saturation, we take the logs of them, then this curve, nice curvy curve, becomes a straight line. And it becomes a straight line because it intersects at the value. This is the saturation of 1. This saturation of 1 is actually this point here. And the rest of this curve is just the straight line. And I'm not sure we'll use it very much in this class, but it's useful because by making this transformation from a curve to a straight line, we can write the straight line very simply just in terms of an equation, and that equation is this. And it says that the effective saturation changes with the pressure divided by the bubbling pressure. So the bubbling pressure, remember, is the pressure at which the bubble of air makes entry. So this is when it's effectively at 100% saturation. If you have a capillary pressure above the bubbling pressure, you'll have less than 100% saturation. And so what it allows you to do is be able to define this curve in terms of this exponent, lambda, which is just the steepness of this curve. And so if you think about it, then what does this mean? You could have a curve that looked like this, or you could have a curve that looked like this. Clearly, if this were a single value of 1, and this was lambda, then this would be small lambda. And if this was a single version of 1, and this was lambda here, I can't go up there, this would be a big lambda. So this is lambda large, and this is lambda small. So what do we think that each of these would represent? If for a large value of lambda, that means as soon as we invade it at this particular pressure, all of the pore space is going to essentially fill up. So it means if the value of this is large, it means all the pore sizes are the same space. You get it in through one pore space, it just invades the whole thing. This means that once you invade the biggest pore, to get it to fill up the rest of the system, you have to really have a big change in pressure to make it invade the progressively smaller and smaller pore space. So this would be a uniformly graded porous medium, and this would be a broadly graded porous medium, one that has a whole variety of pore sizes in it. And so we can use that to characterize these systems. And so, yeah, that's really. And so if you look here, this is a figure that defines these systems. Not very well, not very clear just because it's a bad figure. But if I write on here, this is the effective saturation. This is the capillary pressure divided by the unit weight of the fluid. This is a log scale. This is a log scale. This is 100% water saturated. Then these curves represent 4 different materials to be able to push a bubble of air into them. So what do you think might be the characteristics of each of these? So for this material number 1, pressure goes in here at a very low pressure, so it has to have some big pores. So this has to be the most open graded pores, and then it fills them. For number 4, it has to have the largest entry pressure, so it must have the smallest pore spaces, biggest pore spaces in it. So you can make a distinction between 1 and 4 based on the bubbling pressures, what you think it would be. So I guess number 1 would be the diameter of the pores is small. No, other way. Diameter of the pores is big, low pressure. The diameter of the pores is small. This is number 4. This is number 1. So these numbers tell you something about that. And then actually it's not a very good choice because they look as if they have the same gradient. But if we switch to the different kinds, then number 2 has a value of lambda which is very steep, and number 4 has a value of lambda which is very shallow. And so this is our number 2, right? So that immediately tells you something about this as well. It's vertical, so it means as soon as it invades the biggest pore, it invades all the pores in the system. So this would be uniform pore size. And this would be what we refer to as a broad gradation. Of pore sizes. So some small, and some large. The smallest one is actually much smaller than this one because of where it sits here. And so it allows us to be able to rationalize things. So I'm not worried about that equation that we had. That equation is the equation of these lines. These curves here represent these capillary pressure versus saturation curves. This is in log-log space, and this is in normal space. These are the ones that we've looked at before. This is the irreducible saturation of water. It is only the drainage curve, but they say exactly what we just said about here. This has a very low entry pressure, so this means that the diameter must be small. This has a very large entry pressure, so the diameter, sorry, other way around, right? Small entry pressure, so the diameter must be large. Once for number 2, you invade the thing, it goes straight across here and it saturates the whole sample at almost no change in capillary pressure. So number 2 is the one we looked at here, which is almost the vertical one. So you can tell something from at least the features from these curves, what their physical characteristics might be in terms of both gradation size, the minimum maximum size pore throats, and also their distribution. So, more importantly, that you get a feel for these things rather than know exactly maybe how to use the equations. Both are important. So I don't think I wanted to say much else. We're running out of time anyway. I haven't stopped for questions, but are there any questions? We had one. Good for you. Nothing? Okay. I will give myself a pat on the back then for either baffling you with bullshit, moving too quickly, or explaining everything so perfectly you just have no questions. Okay? So, well, we covered all of those. So I think the thing we'll talk about next time is how we might use some of this information to say exactly what amount of kind of supernatant fluid can we have sitting on top of these capillary barrier lenses. Because that's important in being able to figure out exactly what the architecture of the subsurface is in terms of these layered, this layer cake geometry that we've seen in these other idealized pictures. So we're still talking about how quickly the fluid gets in the first couple of months. It goes in there as quickly as it can. It gets held by capillary forces and then cannot move. We've said nothing about the rates at which we might expect it to go in, which is a topic a couple of down the line when we'll start talking about multiphase flow, but talking about permeability to try and explain that. I'll stop. I shouldn't say we stopped, then I keep on going. Nothing?